Hello. You guys are good? That's enough? All right. Good afternoon. My name is Dan Berteris. Welcome to the NJIT Makerspace. I'm the Executive Director for Experiential Learning at NJIT. So I look over all of our hands-on learning at the college. So if you're interested in anything hands-on, come talk to me. If you want to do anything fun in the Makerspace, you can see the staff here or talk to me about other opportunities that we have. I'd like to tell you about a few things that we're doing new. Is we have some summer courses running in the Makerspace. We have courses in woodworking, welding, and CNC machining taking place over the summer. And we also have a full suite of courses in prototyping, 3D printing, CNC machining, and manufacturing taking place here in the fall. And most of these are general electives, so you can usually fit them in most of your degree programs if you'd like to take them in the fall. So I'd like to introduce Matt Campbell and Matt Cochran, who are both additive manufacturing professionals that work for CAD Dimensions, and they're here to give you a foundational understanding of the state-of-the-art technologies in plastic additive manufacturing. So let's welcome Matt and Matt.
Thank you, Dan. So Matt and Matt, pretty easy to remember. Thanks everyone for coming today. I have quite a bit of content to show you. I think what's over there is probably more important than what's up there. So I'm hopeful we can all get your hands on those parts and answer any questions you might have. So who are we? My name is Matt. I've been working in additive manufacturing for about 4 years. Prior to that, I was at Binghamton University studying mechanical engineering and got my hands on 3D printing during school, like I'm sure many of you have, and just fell in love with it. You know, I always like making things, and I didn't have a CNC machine or even power tools growing up, so it was kind of hard to make stuff. But with 3D printing, you can virtually make anything. This is my colleague, Matt.
I've been working in additive about 6 years now. I work with both schools and industry, helping them select the right equipment. So there's a lot of different 3D printers, different technologies. So just trying to find the right fit for the different applications.
And so we work for CAD Dimensions. And CAD Dimensions is a design, consulting, and additive manufacturing firm. And we represent several different products, softwares, and hardware. Some of them you can see here. SolidWorks is how we got our start as a partner with SolidWorks for over 30 years. We provide the software, whether that's just SolidWorks Basic or Simulia, simulation or electrical, all the SolidWorks portfolio. We also represent Creativeform for 3D scanning and use softwares like DesignX from Geomagic. But more importantly, we represent Stratasys. And that's what we're here to talk to you about today. Stratasys is just one company that makes 3D printers. There's a lot of companies out there that make them, but that's where our specialty and expertise lies. So that's what we're here to talk about today. So simple agenda, a lot of slides, but simple agenda. Give you an overview of the technologies that I work most closely with, as well as a broader scope of all of the technologies that are out there today. Different applications, what I've seen, what we've used with 3D printing in industry, and then parts. A lot of different examples. Each one of those parts has a story behind it, a success story or a solution story, because at the end of the day, we're in the problem-solving business. So first, I wanted to set the stage and just go over some things you already know, so we're all talking about the same thing. Conventional manufacturing is subtractive. You start with a chunk of metal and you cut it down. 3D printing is an additive process. That's why it's called additive manufacturing. More on that note in a minute. There are several unique 3D printing technologies, both polymer and metal. I only have experience in polymer right now, so that's going to be our focus today. Metal is getting there. There's a lot happening in that space right now. And I think with time, we'll start to see metal printers become more common. So we use common thermoplastics in contrast to thermoset plastics. Thermoplastics you can remelt down and use them again. Thermosets you cannot. An analogy I like is thermoplastics are like butter. You can melt butter down, and then once it cools, it can harden again. And thermosets are like pancake batter. It starts as a liquid, and then once you add heat, it solidifies, and you can't go backwards from there. So photopolymer resins. Some common metals, again, haven't worked with them much, but just to show you what's out there. Tool steel, titanium, copper, Inconel. There's a lot going on. And then design for additive manufacturing is critical. I don't have a lot to go into on this specifically, but happy to talk more later. And I put the asterisks there because it depends what you're making. If you're prototyping something, you're going to design it for that end-use manufacturing process, which might not be printing. But if you are going to use printing for volume production, then you want to design it for the specific printer and material that you're using. Yeah. You want me to hold this? Yeah. Okay. So back to one of the first points. Is it 3D printing or is it additive manufacturing? You might have heard these terms tossed around and gone, what's the difference? I'm here to tell you that there really is no difference. It's more about the context of how you're using it. So, additive manufacturing, when I'm at, say a Boeing facility and they're producing parts that they use on planes, that's manufacturing. And the process by which they're manufacturing the parts is an additive process. So that's additive manufacturing. However, we don't often say, oh, I additively manufactured that. It's kind of a tongue twister there. So we'll say, oh, I 3D printed it. So really, they are one and the same. And 3D printing is kind of the more commonly known term. I know when I got started, I wasn't really sure what additive meant. Obviously, it makes sense pretty quickly. But there is no big difference between 3D printing and additive manufacturing. So you'll hear me use those terms interchangeably. And really, now you hear more people just saying I printed this, not even 3D printed this, because we all kind of know what we're talking about. So different technologies. Right here, this is from through the 3D Hub's website, and this is just kind of shows the landscape of all the different technologies that are out there. Again, I'm not going to go into each and every one, but there's a lot of development happening, and kind of the way it works is, whoever invented the technology can come up with their own name, and they might patent that. So in the case of FDM, that was originally patented by Stratasys. The generic term for FDM is fused filament fabrication. So some of these other technologies like SLA or DLP might be the generic names, but you might see them called something different in your research, and that could just be that the company, that's what they decided to call it. So with Stratasys, there are 5 core technologies: FDM, Polyjet, SLA, DLP, and SAF, selective absorption fusion. So I'm going to touch on all these, and you can't talk about 3D printing without talking about FDM. I'm sure that's something you're most familiar with. That's how I got my start, was with FDM. So a few points on that. It was invented by Scott Crump in 1989, and he went on to found Stratasys. So not that long ago was this technology invented. I have had the pleasure of meeting Scott Crump, pretty cool guy, very eccentric. You kind of have to be to get into this stuff, I think, and be very creative and imaginative. I like to say it's the most common, safest, and cost-effective method of 3D printing. I think that statement is debatable, and I think it could change over time. Thermoplastics, not thermosets. And then there's just a list of materials. That is not an exhaustive list, of course. These are some of the ones I commonly work with. Different nylons, polycarbonates, ABS, ASA, TPU, Altem, Peaks and PEX. There's a lot out there in the world of thermoplastics. And it's nice because they all have names we might be familiar with. In the resin space, the companies kind of name them whatever they want. And the chemical composition might be a little unknown. Here's a quick just animation of how the Stratasys 3D printers work. So they have 2 spools, one for model material, one for support material. And those feed up into the printer and through the 2 dedicated extrusion nozzles. So the drive wheels force that material down. And then you lay your support, lay your model. I see a lot of FDM printers up there, so I think we all know how that works. Stratasys does have a soluble support, which is nice. So for complex geometries and different types of parts where getting the support off might damage the part, soluble support can save your life there. And these printers are pretty fast. So are the bamboos. There's some support removal. And there's that soluble support process. You rinse the part off, sand it, polish it, whatever you might need to do. So some common applications that we see with FDM in industry: prototyping is the bread and butter. It always will be. You want something tomorrow, throw it on the printer and get it. You want something in 2 hours, throw it on the printer. Tooling and manufacturing aids. A lot of the things you'll see around here are different types of jigs or fixtures, the parts that are used to make the actual products we might buy on the shelf or use every day. So that is almost as common as prototyping is tooling and manufacturing, especially with FDM. Large parts, some of the other technologies, you see a lot of small parts on here. Making large parts might be a little prohibitive, but FDM excels in that. And then low volume production. If you need maybe 500, 1,000, 2,000 parts, FDM could be a good fit. If you need 20,000 parts, we might look at a powder bed fusion technology, which you'll see later. If you need 2 million parts, you should probably look at injection molding. 3D printing is not going to solve every manufacturing need. The traditional processes you see today are still going to be used and are commonly used. But it's not a question of can you print it, it's should you print it. Here's one example. You can see the end effector over there, printed in Altem 9085. So the story here, Genesis Systems Group, they had a line of robots picking and placing parts, and the tool for that robot, the end effector, was very heavy. It was metal, had a lot of complex pneumatic lines running around it, and it was expensive to produce. So they looked at other solutions, looked at FDM 3D printing. They were able to consolidate that assembly and integrate the pneumatic lines into the end effector itself, produce it faster, produce it cheaper, and more lightweight. And so with a more lightweight tool, you can move that robot around faster, and there's less of a concern of it damaging your actual product. So this case study has been around for a long time, and is kind of a textbook example of how 3D printing is used within jigs and fixtures and tooling in manufacturing. This next one, United Launch Alliance, a space company. So this is all about consolidating assemblies, and that's sort of a design for additive methodology. Is your traditional part might be 20 components, however many, but with 3D printing, because of the nature of the process, the soluble supports, you can combine those together and print it all in one go. So this job went from 140 parts down to just 16 parts with the Altem material. Altem we commonly see it in aerospace and defense. It has a very high heat resistant. It has certifications that other materials don't have, and more importantly, it has traceability. So if something does happen, a part does cause a failure, they need to be able to trace that back to where the material was manufactured, what printer it was manufactured on. All those details are important once you get into aerospace. So that was FDM. Now we'll talk about vat photopolymerization, which is a complex term for SLA or DLP. You have a vat of photopolymer resin. Polymer plastic, photo means activated by light. So back to that original chart, you can see there's 3 different ones they list here. And that chart is a little bit older, and it's not a full breakdown of all the different technologies. Continuous digital light printing, I don't have much experience working with, but DLP and SLA I do. DLP is what I'm most commonly familiar with. But I'll kind of break that down and talk about the differences. First is digital light processing, DLP. The Stratasys term for that is P3, but generically it's DLP. So what's happening here, it's originally developed by Texas Instruments, Larry Hornback, back in 1987, so around the same time as FDM. With this process, a projector sitting underneath the printer, you can see the diagram there, shines through a lens, then through a digital micromirror device, and then up into the resin vat. And so what's happening is it's projecting the entire slice in one exposure, the entire layer in one exposure. In contrast to SLA, which I'll show you a little video, is tracing it out with a laser. And so this technology, specifically the one from Stratasys, has a unique pneumatic separation mechanism. One of the challenges we see with this kind of printing is the parts sticking to that tray sheet on the bottom. Printing a cylindrical tube is not so possible, especially if you oriented it vertically, because all those forces inside are going to cause it to just stick. All the vacuum forces cause it to stick to the tray sheet. But what Stratasys did, and they patented it, is this pneumatic separation mechanism. So what happens is it actually pumps air underneath the tray sheet to inflate it slightly, creating a bit of a bubbled surface to decrease the force required to remove it in between layers. So that makes printing like large blocky parts or hollow sections a bit more possible. Some of the materials, or at least the characteristics of them, I didn't necessarily list them because it depends what supplier you're talking about. Loctite has a lot of materials, 3172, 3955, 3843. These numbers don't really mean anything until you're working with them, but they're all a little bit different. There are elastomeric parts as well. We have some here today, but they have excellent isotropy. So one of the challenges with FDM is the mechanical properties in different directions, depending on the build direction. That is not so much the case with this technology. It prints solid all the way through. Can't really do an infill because the resin will just get trapped in there. You can add a little hole and drain the resin out afterwards. But one of the strengths is the mechanical properties over time, especially. SLA, those parts can get a little brittle over time, not as durable. DLP is fundamentally a different process. And there's the Origin 2 from Stratasys. I put the build sizes up there just to give you some context. If you saw before, that Fortis F900, very big, large parts. This one a little bit smaller, 7.5 by 4.25, but it is really tall. So you can't necessarily print large parts, but you can print a lot of small parts by stacking them up in the Z direction, applying your support structures in between parts. There's an example later where they're able to print 50,000 parts very quickly. And then with this process, you do have to wash the resin off, isopropyl alcohol, there's some other solvents you can use, let them dry, and then cure them. So they're not fully cured right off the printer. Here's showing that pneumatic separation mechanism. Build head comes down, 4K projector through the digital micromirror device shines up, and then it inflates that tray sheet so that the part can remove with minimal forces, giving you the best surface finish possible. So that was just a short one. Some common DLP applications in industry. There's a lot of applications across any 3D printing technology. One of the things I do the most with the role that I'm in is someone comes to us with a part file and says, hey, what should I use? Should I use FDM, SLA? Should I even print this? What material should I print it in? And there's usually more than one answer. Sometimes there's not. It could be very material dependent. That's usually where you start. Well, what material do you need? How are you traditionally making this? What are the requirements? What environment is it in? Is there chemical exposure? How big is the part? If they had a 20-inch part, that puts DLP out of the question. So some common ones we see, housings and enclosures. Those are the camera housings in the printer itself. So they do drink their own Kool-Aid. They print parts for the printers. Clamps and ducts. Those are clamps for an F-16 hydraulic lines. Gaskets and seals, especially with that elastomeric material. If a business is using 1 million gaskets a year, probably not going to print them. But for a lot of the early product development or short-run production, and you need a unique gasket that might be very expensive to have injection molded or otherwise, it's a great application for DLP. And connectors and adapters. A couple more. HVAC components, so anything that has air or fluid flowing through it. Handles and grips. And then medical components, and I have a couple more pictures on that after this. These are nasal swabs. During COVID, we needed a lot of nasal swabs, so Stratasys printed them. And it's in a medical grade material that is compatible with contact with the skin. And during a supply issue, they were able to fulfill it. I think there's like 500 of them on that build, and that build is probably less than 8 hours. So you can run a couple of them in a day and get a lot of parts out. This one from Flowsonic. So this is a hair lice removal tool. So it's not a very high volume product. There's not 20 million hair lice removal tools used every day. So they look to 3D printing and a combination of those materials from Loctite, medical material for the end effector that's contacting your head, and then some durable and heat-resistant materials. And they were able to develop this whole product and print a majority of the components. So for a lot of short-run production or early product development, just getting the parts out to market, getting your designs tested, 3D printing is it. And then aerospace, that example I mentioned earlier, this is from TE Connectivity. They make a lot of connectors for a variety of industries, a lot in aerospace as well. They injection mold, I think, the second most amount of plastic in the world. Number one is Lego. So they make a lot of parts. And their need was 50,000 parts, and it was a pretty short time span, like less than a year that they needed them. And 50,000 is not a very large number for injection molding, and so the cost of that tool might be very expensive, and it might make it unfeasible to do it. But with the 3955 material from Loctite, which is flame, smoke, and toxicity rated, they were able to make these cable holders here that are used on helicopters. Some of the accuracies, plus or minus 3,000ths of an inch. That's about what we can see, maybe a little bit lower, 2,000ths of an inch. Really depends on what you're printing, what the geometry is, but we're starting to compete with machining. So this quick little link here is just to show you the SLA process. You saw how the projector shines the light underneath, and that cures the entire layer. SLA is tracing with a laser. And there's a few different versions of SLA. There's bottom up or top down. That's just where the laser's coming from. This is top down, which we commonly see in industrial SLA. So this video is very old because the technology's been around, but you'll just see that the animation, the laser tracing it on top, and then that build platform moves down into the resin. So it's constantly in resin as it's printing, and there is a wiper that wipes the layers until it comes back up. So that's really all I wanted to show you with SLA. A couple notes on one of the applications we see most commonly used in SLA, aside from just large-scale prototypes. I have seen like whole car bumpers printed in SLA. You'd never put it on a car and drive it for years. It just wouldn't last that long. But during product development, saves a lot of time and money to just print it. And that application, first, this is the Neo, the Stratasys one. Very, very large. So we're not talking about, small parts. Probably not a good fit for it, but a lot of small parts maybe, or large parts. But that application is casting, whether it's investment casting or sand casting. I see investment casting a little more common with SLA. But normally they'd have to use a different method to produce the casting pattern. But with 3D printing, this is kind of what the process looks like right here. So you 3D print the pattern, the geometry of the part that you actually want, and then you assemble the mold, build the shell. It gets put into a slurry, like a ceramic slurry that coats the 3D printed parts, and that's kind of what provides you your mold, and then you burn out the 3D printed part, and then pour your metal into it. So this is kind of the bread and butter of SLA, at least in manufacturing and tooling. Those are the vat photopolymerization processes. Again, I have more experience with DLP. We have an origin system in our office, and there's a handful of parts there that we can look at later. Next is the powder bed fusion. So I've been working with powder bed fusion for only a couple of years now. It was brand new to me. At first you might think, oh, powder. Like, what's going on there? Is it safe? Is it cost effective? It is, and it can be. And when it comes to producing a lot of parts, this is the technology that's really driving it. It's competing with injection molding. I do have a chart coming up that'll show you kind of the break-even point of when you should injection mold versus when you should 3D print. And of course, that depends on what you're printing. But back to that original slide, just to set the scene here. There's a few different powder bed fusion processes. I included binder jetting in there because I have a couple videos just to show you what's happening, the difference between those processes. Binder jetting is not a technology I commonly see as much anymore. It uses it's kind of like gluing the layers together as opposed to fusing them or melting them together. So generally speaking, the parts are not as strong, not as durable, can be a little more porous. The one technology that's not up here because it is outdated is the new technology from Stratasys called selective absorption fusion, which I'll talk about. But you may have heard of multi-jet fusion from HP, very similar. Selective laser sintering. I'll show you the difference between selective laser sintering and SAF technology because there is one. And then you get into some of the metal processes like DMLS or EBM. DMLS is very common for metal, and I think that's the technology that they're focusing on the most right now. But binder jetting versus SLS versus powder bed fusion. So first, if we look at the binder jetting video, so like I said, it's basically gluing almost the parts together. And one of the unique things about it, you can do like multicolors. You see a lot of multicolor parts up here. That's a different technology that I save for last because it's probably my favorite. But there is a video here on binder jetting. if you can click on that link. And then we'll just look at the selective laser sintering video, just so you can see what's the difference between what's happening here. Always forget about ads. So how does binder jetting work? This is from the company Voxeljet. They were one of the original inventors of binder jetting. And really, it's just the middle section that's most important. But sometimes you use plastic. Sometimes they use sand. Binder jetting with sand is common. Everything starts with a CAD file. Most of the parts you see here, I did not design. And I like making the parts more than designing the parts. It's a little more satisfying. But like anything, you have to design the parts. So here, binder jetting, it's jetting down sort of this adhesive agent, and then it's recoating it with powder. One thing you'll see common between all these three different processes is the recoating phase with the powder. And then the build platform lowering, recoat with more powder. And that's really all I wanted to show you with that. So next, if we can look at the SLS process, you'll see a video. I believe this one is actually inside the machine. And SLS, like it in the name, uses a laser. So binder jetting, it's using an adhesive agent. SLS is using a laser to actually fuse the parts or sinter the parts more accurately. So you saw there the laser tracing out all the different parts and then recoating it with the polymer. There's a lot of materials with SLS, more so than the selective absorption fusion process. There's nylons, glass-filled nylons, polypropylene is coming, TPU, so elastomeric material. But that's SLS in a nutshell. So using a laser, fusing the parts. Next, in the slide itself, there's a video at the bottom there showing a run of our printer, the H350. I think I took this video. And this one is very unique, so I have a handful of slides on it to show you how it's a little bit different than the other technologies. But that one slide on the right was just jetting out the fusing agent. So this technology has print heads in it that jet the fluid onto the powder, and then the next sled coats it with more powder. So similar to the other processes, recoating with the powder. So getting more into that technology, powder bed fusion. Stratasys, their branded term is selective absorption fusion, or SAF, and this is what's happening in the machine. Like you saw, the two sleds, they move from left to right, but they're only printing when they move from left to right. So there's nothing happening when they index back to home from right to left. And there's a reason for that, which I'll show you. The fluid is called a high absorbing fluid. And what that does is, it allows it to absorb heat. So when those infrared lamps pass over, it brings that material up to its melting point. So it's fusing down to the layer beneath it. This is just another animation to show you what's happening there. You can see here it's jetting the fluid. So the white is the powder, and then the black is where the fluid's been jetted. And it's only jetting in the geometry of the parts. All of that excess powder that doesn't have fluid on it, nothing really happens to it, and it serves as your support material. So it's a lot of fun to print with this technology because you don't have to worry so much about your support material. FDM, it can be a hassle. You have to get creative with how you orient it. Orientation is not as important with this technology. There are different nuances about that depending on what you're printing. But this is what, this was happening with the H350, recoating the powder. And then any of that excess powder that ends up on the right side gets recirculated back into the machine. And then any of the powder that wasn't used, you can break it out and reuse it and refresh the machine with the used powder. And Stratasys just came out with a kind of software upgrade called Relife PA12, and that allows you to use any nylon powder from any printer, whether that's SLS or MJF. So any excess waste powder that you normally wouldn't be able to print with, you can print with on this machine. And that's just what the depowdering process looks like. This is the manual powder retrieval station. They did come out with an automatic powder retrieval station. You throw the whole cake, as we call it, into the unit. It shakes it real good, gets most of the powder off, reloads that powder into a container so you can refresh the machine. And then the next step after that would be finishing and bead blasting. So the workflow for that, you get the parts out of the powder retrieval, and then you get into your finishing. So no matter what, you'll have to bead blast the parts because you're not going to get all the powder off when you're doing your post-processing or powder retrieval. And you don't want to because some of that powder that's just right at the surface has experienced a little more heat than the rest of the powder, so it's a little bit aged and wouldn't necessarily print as well. But once you get the parts clean, via glass media is what we commonly use, then you have options. And those options are very application dependent. You'll see a lot of gray parts here. Those are the SAF parts. And I like to say they're good for under the hood components. If nobody's ever going to see the part, who cares what color it is? Although what I commonly see is people still like their parts dyed black. But you can dye the parts almost any color, but you're starting with a gray part. So not all the colors look perfect. And you can do different processes as well. Just like FDM, you can drill into the parts. You can put heat set inserts, tap for helicoils. Like I said, dyeing the parts. And this is the key difference between SAF and some of the other powder bed fusion technologies. And that difference is the time in between layers. So every part, whether it's in the bottom left-hand corner of the build or the top right-hand corner of the build, is experiencing the same amount of time in between layers and the same thermal experience. And that's very important for the quality of the parts. If you print 500 parts, but only 30 of them are in tolerance, that's a waste. You might as well injection mold them. But this is kind of the key difference is that homogeneous fusion, recoat, heat, print, fuse, and the uniform thermal experience. The three materials right now with SAF, a few notes on those. First was PA11, so it's a biosource material. I do have a part over there that shows it starts with the castor beans, then it goes to oil, and then it goes to the powder, and then you get your part. So it's a much more sustainable material than some of the other polymers we use. PA12, nylon 12, one of the most commonly used plastics, has the best accuracy with this technology, a little bit higher stiffness and less warp than PA11, and a higher heat deflection temperature, and it's known and trusted. And then lastly, the most recent material is polypropylene. Has the best chemical resistance, so we'll see it used a lot for like filter housings or even like components that are exposed to gas or other solvents. And it's the lowest cost per part. Another big use case with this technology is orthotics, and polypropylene is a very common material used for custom orthotics. And we know of a company that's using this technology to print those custom orthotics day in and day out, exactly the way that the patient needs. There's the H350. I have like a little version over there, like a miniature. And the build size, we like to say it's about 2 shoe boxes stacked on top of each other. So it's not the largest powder bed fusion printer that's out there, but because of that uniform thermal experience, it allows you to nest more parts into the build. So you'll have be able to put more parts in the build, and the part quality will be better. The accuracy in between parts will be better. Automotive is one of the major applications for this technology right now. So in addition to under the hood components, we are seeing it used in tooling applications. Honda has one of these, and they're printing masking fixtures. So these metal discs that they shot peen, there's areas of the part that they don't want to be shot peened. So they print out the disc, cover the part, the beads hit the plastic part, protects the actual product underneath, and they use, print hundreds of those every month or so. Here's an example, electrical insulated connectors. What you're seeing on the bottom, the raw gray part on the left, and then on the far right is a vapor smooth part, so that's another additive or another post-process you can do. And then in the middle there, that one was just dyed black. So this is showing you can fit 384 parts or 192 pairs. That's a 23% nesting density, which might be a little high for some other technologies, but this one, it can accomplish that. And $4.75 per pair. And it's always cool to see all the parts kind of nested inside. And for comparison, FDM versus SAF. So this is the same part printed on an F900, that large printer I first showed you, versus the H350. So on the F900, you can fit 176. On the H350, you can fit 198. So you might think, well, it's not a whole lot more, but it's really about that time, right? We know FDM is fast, but not when you're printing 176 parts. This build took a little over 15 days to get all of the parts. On the H350, that's a 12-hour print time. There is a cooling process. It's usually twice as long as the print time. So in 36 hours, you can have all 198 parts versus waiting 15 days with FDM. So that's kind of where SAF, the key differentiator, the strong suit of the technology, is when you need a lot of parts and fast. But not every part is good to print in SAF. You know, that end effector from Genesis, not a good fit for SAF. You know, if you need 50 of those, that's going to be 50 builds. Even I don't think that would even fit in the build. But that's where FDM is a better fit. And here's that comparison to injection molding. So normally when I go through this, I show 3 different examples. One is a very complex part, one is a large part, and then there's this one. Now with the reason this one is a good one to show is because it gives you a good idea of what the break-even point is. So for small, mildly complex geometries, it makes sense to use SAF until the quantities are very high. The blue line is injection molding, the orange line is SAF. Notice how our cost doesn't change no matter how many parts we're making. Whereas injection molding is, as that quantity goes up, that cost goes down. But there is a break-even point. So right at around, 50,000 parts, that's when injection molding becomes a little bit cheaper. However, even at 68 cents versus 96 cents, maybe you still want to print it. Maybe there's a chance the design is going to change, and that would have to cause you to have to recut a mold. So cost is not always the reason to pick between one process or another. There's more factors at play. This company, Rivian Robotics, used SAF for some of the components on their robots itself. And that's what these components look like here. So they integrate some of the electronics into the parts, and before they might have machined those. Don't really need a lot. It takes a long time to get them. A lot of reasons that 3D printing them made more sense. This next one I think is pretty cool. I want one. This is a sleep mask. So it sends electrical signals or auditory or visual signals while you're sleeping to trigger REM sleep. So for those that might have trouble sleeping, that's really the main application. But it can also help induce lucid dreaming, which is where you're aware that you're dreaming, which is cool. And this is one of those products, again, they're not selling them like Lego, you know, or like computer mice. There's only a handful, and they're very specialized product. And one of the key benefits of using 3D printing in the end-use process is that they could prototype and develop in the same technology as they're producing, as they're manufacturing in. Because normally you might 3D print something and then go to injection molding, and you find all these issues, all these different concerns about the design because you hadn't injection molded it yet. But with 3D printing, you know exactly how it's going to come out from the very first build. And so that product development can happen faster and cheaper, and it's just more effective. And lastly, and one of my favorite, I know it's Matt's favorite, is Polyjet, or material jetting. So material jetting, I have an animation to show you, and the sort of branded term from Stratasys, the technology name is Polyjet. And that's all the full color parts that you see on the table here is material jetting. And let's see, developed by the Israeli company called Objet in the late 90s. And then in 2012, Stratasys merged with Objet, and that's when they changed the name to Polyjet. So there's still a handful of machines out there under the Objet name, but Polyjet is the new name for the technology. Let's see, play that again. So the build head has like 4 different print heads in it, and there's nozzles on those print heads that are very, very small. And what it's doing is jetting the fluid out and then curing it with a UV light instantly. And when it's jetting that fluid, it's combining the colors together. So it's like a 2D printer in that you have your cyan, magenta, yellow, white, black, clear in this case also. And it's combining those colors together during the print process to achieve virtually any color you want. You can set RGB values, hex codes, and also Pantone validated colors as well. So color accuracy, if that's important to you, this is the technology that can achieve that. Now the materials, they are thermosets, same as DLP or SLA. They're fairly brittle over time, so these aren't really not parts you might use for a long time or see on the shelf necessarily. Some of that's changing with the fabric printing. One of the things you can do with this technology is print on other objects. You see you have like a metal sign there with our logo on it. That was printed directly onto that sign. You CAD up a jig to hold it in, CAD in the actual sign itself, and then the letters. The printer prints the jig out, it pauses, you put in the metal piece, and then it prints over it. Very similar process for printing on fabric. That's the largest Polyjet printer that they have. And a lot of it's product design and development, getting CMF models, color material finish, in the hands of, say, the marketing team or the sales team or just the engineering team to say, okay, here's what our product's going to feel and look like once we, make it with, say, injection molding or otherwise. One of my favorite parts is the banana. It looks like a banana. It feels like a banana. It does not taste like a banana. So some of the common Polyjet applications, rapid prototyping. It's a fairly fast process. Within a few hours, you can have your part in hand with all the color on it. The parts are fully cured off the printer, so there is no washing and curing. The support material can either be dissolved or jetted off with a water jet. And then there's a lot of post-processing you can do as well. Some of the pebbles, if you come up and see those later, they'll look really shiny or really clear. Those have likely been sanded, wet sanded, and then clear coated afterwards. It's a fairly soft material, so you can work with it. Medical and dental, especially in the education space, is a very big application for Polyjet. Whether it's emerging surgeons that want to practice, performing a surgery, it's less expensive than cadavers, and a little safer as well, or just teaching, showing, hey, here's what's happening inside your head. I'm still trying to figure out what's going on in mine, but either way, it can show you you can see through the clear material into the full colors, and we've worked with a number of schools, especially in the medical space, with this technology. Getting those realistic parts in your hand. We have some bone-like material. There's what's called a bone matrix material. It feels very similar to bone if you're like drilling it. There's also a tissue matrix material that feels very similar to cutting skin with a scalpel. And then small detailed parts. The layer heights on Polyjet is around 19 microns, in contrast to FDM, which we might print at 5,000 7-inch, 10,000 7-inch. The layer height is very small. So this replica of the Mayflower ship, those sails are like paper thin. And we have one at the office. It probably wouldn't survive if I brought it here. But those sails are really thin, and doing anything really fine detail with a lot of obviously color, this technology is it. And then what I call low intensity tooling. So I do have one example sitting on the table there of an injection mold. Now the DLP technology that I showed you earlier is starting to take over for this application, printing out injection molds because some of the high temperature resistant materials can withstand that process. But the digital ABS, which is the name of that material there, can also be used. And you're not going to get a million shots out of these molds. It's just to validate the mold design. Molds can be very expensive to manufacture. So if you can get one in your hand, test out the part, see how the part comes out and feel it, it's going to be a much cheaper process, and it'll speed along development. Just some more pictures. I do have that N64 controller up there. Greatest console ever made. Realistic product packaging. So there's a good story with, they worked with Bullet Bourbon to produce the bourbon bottle, and they handed the president of the company a printed bottle of the bourbon, but they didn't tell him it was printed, and he was like, why are you handing me a bottle of my own bourbon? And it took him a minute to realize, oh my, this isn't real, it's printed. And they can mimic sort of the liquid effect in the print itself. That one up there is the J55, and that's more of an office-friendly type printer, so a little bit slimmer, slicker profile. And we use that one, I use that one a lot. I just wanted to call out this company. So I worked with them for almost a year to prototype these parts and see if this is going to work for their process. They're called Fourth Seal Studios, and they make realistic eyes for film industry, like costume design, model making, anywhere where you might need a custom eye, but either it doesn't exist or you don't want to pop someone's eye out. They 3D print them. Now before, they were using a more complex process. They still printed the core on a SLA machine, but then they were actually hand painting all the veins, dropping in like a handmade iris, and then coating the part with a clear coat. And their business was starting to grow, and it was very time consuming. There's only a couple of them on the team. There's more now. But it's very time consuming to paint each individual vein. Sometimes they would use yarn to lay down the veins. But they said, hey, we see this technology. We want to know if it's going to work for us. And we prototyped a number of different eyeballs. I printed a lot of eyeballs. And eventually, it got to a point where they said, yeah, this is it. This can work for us, our customers. It's going to work for our customers. It's going to work for the film industry. And so that one's like the size of a hand, very large. And so they have a J55 sitting in their garage in Pennsylvania. And this was one of the cooler applications I got to work on. Now, the real more challenging part, in my opinion, is not pressing print. It's the design aspect for this, because there's a number of softwares that you need in order to make this happen, and there's different workflows you can use. You might use a software like Keyshot or Adobe Substance Painter, and import your different textures and wrap them around that solid model and achieve what you see there. And then I like these guys too. A little Pokemon. So I'm pretty sure that's all the slides that I have. If you want to look at some of these parts, I can call out some of them. This one here is the pick guard for a fender. So I don't have a fender yet, didn't bring it with me. But what you're seeing here is the topography of Mars laid onto the pick guard. So feel free to come up later and touch it. It's a nice print because it doesn't take that long, doesn't cost that much. It's not a lot of material, but it can really make a guitar stand out. Matt, if you want to pull out that mini end effector. So there's the larger one there, but the small one, you can see they added some hardware to it. Some of the medical models. Like the inside of a heart. You'll see they added magnets to it. So I don't know if you have the other side, but it's one thing to look on the outside of a heart, but it's another thing to be able to open it up. And so whether that's just for training purposes or even pre-surgical planning, they might, print this out and then go to the patient and say, hey, here's what we're going to do, which always makes the patient feel more comfortable.
This half is the material called tissue matrix, so it replicates human tissue. So you have the realistic visual, but then you also can get the haptic feedback. So I'm working with the hospital in Boston that is looking into this technology to print mitral valves, so their med students can work on repairing damaged mitral valves rather than using cadavers or an animal or whatever they're currently using. They can just print them off as they need them.
The apple's printed as well. Don't want to break a tooth. This banana is printed. And then I did want to call out that wire harness board. So this is common in automotive. There's a lot of wires running through your car, and one of the processes that they do is lay out all those wires so that they are in the right spot. They'll do it on a board like that and see where the wires are going to go. But one of the parts they need is something to hold on to the wires. And sometimes they're standard parts, but a lot of times it's a very custom-made design. And so injection molding, like just a couple thousand wire harness fixtures, is a little bit prohibitive. But with the SAF technology, they can print them out, customize them exactly how they need. And I just think this one's cool because anytime you can see printed parts with other parts, other real like metal parts or wires, I think it stands out. That's that. Someone was able to export a chunk from Minecraft and print it in Polyjet. So in theory, anything you could design in Minecraft, you could pull it out and then print it. I've always thought that one is cool. And then the fabric pieces. So this is some new stuff, and Stratasys, I think, is really the only one doing it. And there's a couple different use cases for this. Obviously, one of them is fashion, doing like custom collaborative designs. There's one where they have like a Lakers logo printed on the hat. This is showing just the different ways you can print it. We've talked to a handful of shoe companies about printing their logos on the shoe itself. Another application is automotive interiors. So not on any car I can afford yet, but some of the more high-end cars where there's custom embroidery on the interior and all that cool stuff going on, starting to look at using Polyjet to print directly onto the fabric before they install it into the car. You want to bounce that ball. So the SAF technology is interesting because it has a little bit of flex to it. Now, there is, if you've seen, Wilson did make a 3D printed basketball. I was able to actually bounce it at a conference last year. And that was a TPU material using SLS technology, I believe. So a little bit different than this. This is just nylon. But, I'll play wall ball with this out back all the time. And this one's a lot of fun. Yeah. So I could go on all day about 3D printing, about these parts. Definitely come up and take a look. I guess one last one, I did bring my putter. So we don't necessarily see 3D printing in off-the-shelf parts all the time, but when I was looking for When I was looking for a new putter, a new set of irons, this one caught my eye right away. Now, if you have seen anything else out there with Cobra, they are printing out of metal now as well, and printing the irons out of metal, printing the putters out of metal. This was slightly before they started doing that, but you feel free to come up close later. But there is a powder bed fusion part, nylon, inside the putter itself. So maybe it's a little bit gimmicky. I thought it was cool working in 3D printing. It caught my eye immediately. But it allows you to lightweight the part a little bit more, or lightweight the putter, and create a design that would be very, very difficult to injection mold. That's one of the key advantages with powder bed fusion.
And it took 3 strokes off his round.
Yeah, and the irons I have the printed backing on them as well. So I'm not sure how long that was. That was a lot of information, so I appreciate everyone hanging in there. Hopefully you learned something. I've learned a lot over the last 4 years in this job about how printing is used, but more than just printing is manufacturing. One of my favorite shows growing up was How It's Made. Just want to know how stuff was made. I couldn't even conceptualize it, like holding like a computer or something else. It's like, how do they actually make this? So once I got into this job, it feels like I'm living that every day. Whether it's going to a school or going to a manufacturing facility, seeing how they're making things and learning about traditional manufacturing is just as important as learning about printing as well. So thank you. Not sure if we're taking questions or anything, but we'll be sticking around, so happy to answer. Any questions? Yeah.
So what organization certifies some of the materials that earlier you said? Hello. I wanted to ask you guys, what organization would certify some materials that you guys use for like specific applications?
Yeah, so like in the case of Altem, it has its blue card certification. And so that's for like UL 94 V0 rating. So UL might be one of the certifications. I know ASTM is starting to get a lot into 3D printing materials and different validations there. Can you think of any others? Not as well versed there, but like I know UL is one of the ones we hear about a lot and use a lot. Yeah. Thanks for the question.
If there's no other questions, you guys are welcome to come up and check out the parts.
Yeah, please do.
mix up the three materials in a single print. So you get a rigid material, you get a flexible material, and depending on how you mix them, you can change the shore values. So as you feel those, you can feel the difference between them. This is, so that's the soluble support material. Yeah, this is a cool one. This is actually an MIT research lab that did this, and some material development that they're trying to do. Twisted bilayer graphene. But yeah, just a cool print.
How much time does it take to manufacture?
That one, I believe,
5-6 hours?
I have the. Because I get that question all the time, and I had to ask someone at Stratasys. So.
Yeah.
7 hours for
7 hours.
one banana. Yep.
I said 5-6
9
hours.
hours for two.